Hey, it is 2 hours UTC, and it's time again for Astronomy Daily Live. I'm back. I'm back as promised. Here we go again. Another run. Do not see do not see anything in the near future that's going to interfere with this daily live stream. So yeah, I'm back for a little while. So, welcome everybody. Come on into the circle, gather around, turn off the TV, forget about all the news. Let's sit around for a while in our on our, virtual porch here, grab our favorite beverage or consumable and sit around and talk about and share a passion, which is astronomy. Cheers. So, this is just a fun, casual get together every single day, practically every single day. Now, I've been doing this for, I'm not keeping track, but I've been doing this for, I don't know, a little over 3 months or so. And I have missed now three live streams. So, not too bad. It's gonna happen, but I purposely have a very dull life, relatively speaking. I'm not running around all over the place. I'm not traveling. I'm not, you know, I am here. I am here. And the reason why I'm here is because this is exactly where I want to be. And uh, with this amazing thing that we're currently calling the internet, there is absolutely no reason for me, at least, to go anywhere at all, because pretty much anything that I want access to, even people, right? Um, I can access this way, and it's awesome. And look, as long as we don't destroy ourselves, as long as we don't do that, then this is only going to get more and more and more amazing. Thank you, Uncle Bill, for reminding me to tweet that Astronomy Daily Live is live now. Tweet. There we go. Da-da-da-da. At least eventually it will. All right, there it is. So, uh, you know, if we don't destroy ourselves, then then this is only going to get better and better and better. And I was thinking about this the other day, and thinking about 1918, 1918, and I mean, I don't know a lot of the details in terms of technology, and where we sort of were inside of our heads. But you know, in 1918 compared to 2018, holy moly, wow, wow. And so, um, you know, if you sort of do a linear extrapolation to 2118, just a linear extrapolation, take sort of the data point that would be sort of the state of the world in terms of all of these things, 1918, and the data point which is sort of state of the world 2018, and just connect those two data points and then extrapolate that out to 2118. It's unimaginable. It's just totally unimaginable. And most likely, okay, I mean, uh, uh, things in this universe don't change well, well, there are things, I guess, that change linearly, but most things change exponentially. There's some kind of power law. So it isn't a straight line. It's a curve, right? And it's unbelievable, um, you know, uh, how things have changed in the past um, 100 years, and it's unthinkable. It's unthinkable. We can't even imagine. We can't even imagine how, um, well, for sure, different things are going to be, um, if we play our cards right and figure out and realize what we have and what we are and what we're capable of doing. It's going to be amazing. It's going to be absolutely amazing. What we're doing now, we're going to look back and be like, God, how primitive. And I mean, what we've got now is really amazing, right? Really amazing. Almost bit my tongue. Um, so yeah, but what we have to do, okay, what we have to do is we have to realize fundamentally that there is enough to go around. We don't have to have these big fights about stuff, these global fights about things. Now, humans are humans, right? So somebody is going, to disrespect you or me, and, we're going to get mad about that, and, you know, want to do some kind of, revenge thing. That's little, right? I mean, it's a big deal still. But, relatively speaking, that's sort of a little thing. I'm talking about the global things. I'm talking about those people with their fingers on the button, right? And those um, um, systems that, I mean, what bothers me most about the bomb, right, is that we're relying, at least my you know meager understanding of things is that we are sort of relying on systems to make sure everything is okay, and it's like, how reliable are those systems? Could some kind of mistake be made? And it just so I'm hoping. See, it's a race now. I see it as a race. Um, not all of us, not all of us have to, you know, get this realization that we're amazing. Not all of us have to, but enough of us do. And if enough of us do, then then it's just going to be absolutely amazing. And there is enough um, to go around. I mean, we have barely tapped our own natural resources, much less the resources of like solar system scale things, much less, galactic. There is a lot of stuff. There's a lot of stuff. And so, one of the first things that I hope, more of us will realize is that, we don't have to be um, fighting over, who gets things, because there's more than enough. There's more than enough. Bucky Fuller, who I uh, greatly greatly admire, he realized this almost 100 years ago. Right? He was talking about this shit back in the 30s, in the 1930s, and you read his book. I don't have it here, not on hand. Um, I've actually got two copies of that book, but it's a book. called Nine Chains to the Moon. Okay, take a look at that book, and it's amazing how, I mean, you know, while it's amazing how many things haven't changed. He wrote that book in the 30s. I think he wrote it in like 1938, and then he revised it a few times. But his one of his mantras is that there is enough to go around, and he talked about this concept of um, um, ephemeralization, and what that is doing more and more and more with less and less and less. And you know he actually tracked that. Uh, he used a bunch of different examples, but like in terms of 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 the tensile strength of steel, right? He charted this, and it's an exponential growth. Um, and it turned out that more and more tensile strength was being achieved with less and less and less material, because we just learn more and more and more, right? And taken to the extreme, okay, you realize that the universe is doing everything effortlessly, right? So that's doing everything with no effort whatsoever. And there we go. So check out Buckminster Fuller for sure. I highly recommend looking into his things. Now, some of his his stuff was it's like whatever, right? The interesting thing about Bucky, though, too, that nobody seems to acknowledge the fact that it was Buckminster Fuller who came up with the concept of Earth Day. Um, Everybody thinks it's this big environmental thing, and blah 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 blah, but it isn't. His idea was, it's like, this is the Earth. Let's go for it. And the environmentalists, bless their hearts, right? Sort of took it over and made it a more inviting, which is very very cool. But it's not all of it, right? It's not all of it. Anyway, I totally digress. I'm going to pull up my chat here to see what's going on. Oh, there's a heavy, heavy chat. Hiptacular, you are spectacular. Thank you, thank you, thank you. You come in here, you've made a splash, you've made an impression. Thanks much. You can come in any single time. Got to go. I had to run outside and scream. We can do it. Yeah, yeah. But look, here's the deal, right? This is what I've realized, is that it's it's exactly sort of what Gandhi said, right? It's like, be the change, be just be it. You know, don't try to convince anybody else. Don't try to win anybody else's heart over. Just do your thing. Do your thing. Realize realize that you are awesome and we are awesome. For some reason, I've got a lot of delay on my end of things. I'm gonna see if that's coming through or not. Yeah, it sort of is. I don't know. It is only 2018, so technology isn't that great yet. So it looks like I'm a little jumpy, but whatever. We're casual. We're fun here, and I'm going to get off of my soapbox. I just, there's enough. There's enough that we can have everything that we want, everything. And if you realize that, then we can move ahead. We can get out of this stupid, ridiculous mentality that we have to fight for everything. It's ridiculous. It's ridiculous. This is the perspective that astronomy brings to me. Is that when I look out into the sky, I see big stuff. Okay, I see big stuff. I see a lot of stuff, and the fact that I can sort of put a lot of the universe inside of this head is amazing. It's totally amazing. So all right, I'm totally off of that. Want to hear about the music festival? The music festival was not well advertised, not well advertised at all. So the turnout in terms of the crowd was pitiful. It was pitiful. It was sad. Okay. Um, there were definitely more vendors than people there, um, like attendees. What we noticed though was that many of the attendees had parked and camped, and were basically just sitting at their campsites, doing what they're doing, listening to the music. So the interesting thing is that um, uh, my musical partner, he plays native flute, and the interesting thing is that when we started, there were maybe three or four people actually watching, actually standing at the stage watching. I've got barking dogs here. Hold on one sec. I just want to. All right. It must just be one of those rare passing cars on my little road out here. Anyway, so as soon as we started to play, um, a pretty good crowd gathered. I would say probably 30 or 40 or 50 or so. So, as I said, that is pitiful. That is pitiful. But um, we had a good time. Everybody said, we sounded good. I am my worst critic. I think everything I do is eh, like that. So my perspective is um, uh, you know um, biased, very very much. So unfortunately, I sort of have to rely on others, to give me honest feedback, because you know even if even if the music is terrible, it's sort of like, good job, good job. It sounded good. Um, you know, you don't want anybody to feel bad, right? Um, so I'm sure there was a little bit of that, but you know, people said it sounded good, and bottom line is that we had a good time. We, totally enjoyed ourselves. The final drumming thing was awesome. I didn't want it to stop. We probably did it for, I don't know, 5 minutes or so, and that definitely was not long enough. Definitely not long enough. So, but yeah, it wasn't well promoted. Um, but it's really inspired me to get back into composition, um, which I've sort of been neglecting a little bit. So yeah. Da, 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 da. Let's see. Long live the crow. Long live the crows. Okay. Uh, yeah. Well, the only reason why I sort of gripe about the size of the crowd is that I like to share. I like to give, right? And I like to give a lot. Um, and so the more people who are there, the more I can give. So anyway, all right, enough of all that kind of stuff. Want to give a huge shout out to a new Discord channel that I just joined. Um, she's Midnicorn, and she, I just um, uh, watched for the first time this morning or this afternoon her live stream on Twitch. It looks like she sort of covers science news, um, and yeah, pretty awesome. I like her. I especially like her because it seems as though her path um, uh, was sort of a different kind of path, not the trodden path, and that is definitely mine as well. So I'm interested in learning a little bit more about her path. I think she's currently working on a PhD. So her path has sort of led her towards having all the paperwork and everything. Mine is not. Mine is not. My experience uh, in school was sort of similar to what she was describing. In that I just don't learn that way. I don't learn inside of a classroom. So trying to memorize things and um, um, regurgitate, right? And so a lot of people are very skilled at that. I am not. I am the opposite of skilled at that. So um, uh, yeah, and it's actually the midnicorn. So that's all one word. Um, uh, Post the link, Uncle Bill. Yep, absolutely. Uncle Bill is going to post that link in the chat so you in the chat can see that. And yeah, very cool. So big shout out to her. She's going to be doing a 6 hour live stream um, in a little while. I don't know if I can uh, pull up the info on that or not. Why is this machine giving me the big red X? Um, she's doing a charity stream. I'm trying to see where or when. Um, uh, well, somebody in chat, let me know when that stream is going on. I'm looking on her Discord thing now, and I'm of course I'm not seeing it. So yeah, let me know when that is happening. Let everybody else know as well. So the other thing that I saw today was, and I'm going to go over to my YouTube channel. There's a YouTube channel that I subscribed to a little while ago. It's called Space Profiles, and I'm not. I haven't really checked them out much, but it looks like what they're doing is they're just sort of highlighting astronomical objects. And today's one was about a star called 119 Tauri, and that got me thinking that I should, and I'm going to tonight or today, uh, um, I'm going to um, do a new segment here. It's sort of a extension of um, um, object of the day, but instead of doing just Messier objects and new general catalog objects, I'm going to extend that to all objects, right? So stars, right? So um, I uh, I did a little bit of uh, um, sort of a trial run, and yeah, Simbad, of course, has all that information on stars too. So let's do that. And the way that I thought that we could do it, and oh, maybe I may not be totally prepared. Well, all right, let's do it anyway. Um, what I thought that I would do, I'm going to share my screen. I know this is very, very exciting. I can hardly stand it myself, but I'm going to go over here and I'm going to go over to random.org, and I am going to have random.org choose for us a constellation, and then and then and then we'll go from there. So the International Astronomical Union has identified 88 current constellations. Okay. So I'm going to have random.org choose a number between 1 and 88. And then I think, let me go over, I'm going over on my Linux machine here. Yeah. I've got an alphabetical list of all the constellations. Okay. And we'll sort of start from there. Okay, so this I'm trying to hit a bunch of things at the same time, sort of talking about different constellations, and then we will pick a a star inside of that constellation, and yeah, we'll see how I'm going to choose that. So, all right, let's choose a constellation first. So between 1 and 88, drum roll, please. 79. Okay, so I'm going to go to constellation number 79, which is Telescopium. Telescopium. Okay, and what we're going to do first is we're going to uh, just look at that constellation. And Uncle Bill, if you want to post some pictures of that in the Discord server, feel free. Telescopium constellation. Wikipedia is our friend in this case. I've noticed that at least the ones that I looked at before, they always have, okay. They always have a picture of the constellation itself. So these are the boundaries of that constellation. I guess. I guess that's how I would interpret that. Yeah. So the white area is the boundary of that constellation, and you can sort of see. Let's see if there's a bigger picture here. I'd really like to have a bigger picture. I'm not seeing one. Anyway, all right. Well, these are the boundaries. Hope you can sort of see this relatively well, but you can see, you know, all constellations sort of follow the same formula in that the brightest star is called alpha, and the next brightest star might be called beta, and then gamma, delta, on and on and on. Now, that's not always the case, and I guess in this case it isn't. I see an alpha up here, but then I don't see a beta. Um, I see I see actually two. What is this? Phi? I'm not exactly sure. Well, yeah, are those the same? No, those aren't the same. All right. I don't know my Greek all that well. There is a delta, there's an epsilon. Anyway, this is a southern hemisphere constellation. You can see down on the bottom here, this is the right ascension, right? Right ascension goes from 0 hours to 24 hours. So you can sort of see, that this is in, sort of the latter part of that. What it's going from about 18-ish hours over to like 21 and a half hours, and then declination. We're going from what about negative 46 to about negative 56 or so. So it's a relatively small constellation. It looks like it's south of Sagittarius, east of Scorpius. So yeah, very, very cool. Um, so now what I want to do is grab my Burnham's Celestial Handbook, the constellation of Telescopium, which of course, um, which is of course the book that I don't have on hand. Let me. I'm going to pause just for a couple of minutes. Let me locate this book. I'm not quite as prepared as what I thought I was going to be, um, because I've got two of the three volumes of Burnham's within uh, grabbing distance, but the third one that I need to find the constellation of Telescopium is nowhere to be seen. So let me see if I can find it really, really quick. If not, maybe we'll just pick out one of these, that we can sort of identify here. So hold on for just 20 seconds. Okay, hold on. Hey, that was easy to find. So here, let me. Well, no, I'm not going to show you this version of my Burnham's because it's just pitiful, absolutely pitiful. So, in Burnham's Celestial Handbook, um, quite a few binary stars are listed. Quite a few variable stars are listed, and quite a few non-stellar objects are listed too. There's a globular cluster, um, NGC 6584. It's a bunch of galaxies, and there's one variable star that they go into more detail on, and that's RR Telescopium. So let's look at RR Telescopium on Simbad and see what we can find, if anything. I don't know. It's a variable star. It says, at least according to Burnham's, it has a period of 387 days and a magnitude range going from 12 and a half to 15. So let's just type it in and see what happens here. Telescopium. Telescopium? Telescopium. Yeah. RR Telescopium. All right, it's calling it a variable star, a symbiotic star. Okay. Well, there again is its coordinates. So 20 hours, 4 minutes, 18 seconds, and negative 55 degrees, 43 seconds. So let's see, 2004 and negative 55, 43. So yeah, it's going to be what, around this area over there somewhere. Um, so let's do the same kind of thing, that we do with other objects of the day, and just go through this and see what we see. Yeah. Um, so here we have a proper motion, um, and I think this is proper motion of right ascension and proper motion of deck in milliarc seconds. MAS is milliarc seconds, a thousandth of an arc second per year. So 0.29 milliarc seconds in right ascension and 3.2 in deck. I'm going to pull my chat back up here so I can see. Uh, yeah. Okay. Um, Joe Anthony, hey. Nice you could drop in. Welcome. We're just looking at a sort of a random star in the constellation of um, Telescopium. This is a variable star called RR. Telescopium just got into it. So it looks like this star, relative to us, is moving towards us at 61.8 kilometers per second. So that's moving pretty fast. Moving pretty fast. Um, Spectral type. Wow. Is this like some kind of weird binary or something? I'm not exactly sure what a WN3-6.5 is. I don't know. Um, but there's also apparently an M star. So that's a pretty low mass star, low and faint and red. These are the magnitudes of the star using different filters. So U, B, and V are the Johnson visible wavelength filters. And yeah, tenth a magnitude or so. But look, as you move into the infrared, look at how bright it gets. Wow. Wow. Now, of course, we can't see, with our own eyes, um, 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 inside the infrared, but it does look like it gets brighter, which makes sense. If it's an M star, then it's going to be a very red star, so it's going to be bright in the red. So definitely a star, visible with a 8-inch scope um, in the visible for sure. Got a bunch of different names, of course. And these usually correspond, to different catalogs. See, like AAVSO is the um, um, variable star observer group. AA. Oh, I don't remember what AA stands for. Let's look really quick. Google is our friend. I think it's the American Association of Variable Star Observers. Is that right? AAVSO, or is it the Astronomical Association? Uh, the American Association of Variable Star Observers. So okay, yeah, they have a catalog number, 2 mass. Even Gaia. It's even in the Gaia catalog. Yay. Wow. So this is a very well studied object. 505 references total. So we'll come back to that. You know, diving into the papers is sort of where you really learn about these guys. Thank you, Tom. Appreciate it. Let's see. Oh, there's some observing logs too. Very cool. All right, let's look at. Let's see. It looks like they have some measurements of velocities. They have some observing logs. We'll take a look at those too. So let's see. They got two measurements, one from 1995, one from 1979, that puts the radial velocity moving towards us, both at 61.8 kilometers per second. So that's a pretty good agreement there. I, yeah, I'm not quite sure what this WN stuff is. Kind of interesting, though. You know, these later um, observations put the star at an M 3.5 spectral type, and then later on at an M7. So there's a little bit of disagreement there in terms of exactly what kind of M star we're dealing with here. So that's pretty cool. I love a mystery. Oh, it looks like too they measured the maximum brightness and the minimum brightness of this star back in 1971. Who nobody else is looking at this star? Come on, people. What's wrong with you? I'm gonna go do it. um, but yeah, that's sort of in agreement with. Well, no, that's not in agreement with Burnham's. I think Burnham's was saying like 12 and a half to 15. So yeah, you know, we'd have to look at the reference itself, which is of course you know a paper. But I'm not going to do that here. If you guys want to on your own, go for it. Let's look at these measurements here. Let's see. Oh, did I do that already? I guess I must have. Yeah, because these are all the observations. I think ISO observation log, the ISO data center, ISO that is. Um, yeah, so these are just observations of this object that have been made, and some of the parameters, right? Like when it was observed, how long it was observed. Yeah, very cool. Let's see if there's any. I don't know. I haven't I haven't looked at this, I guess, hard enough to really know exactly. Let's just click on this thing. Oh, it's a spectrum. Cool. So yeah, this is a spectrum in the infrared, right? Because we're talking about microns here. One micron is like 10,000 angstroms. So we're talking 10 microns, 20 microns. So this is thermal infrared. So they're actually measuring, you know, the heat from this star. Yes, you can measure the heat from stars. And yeah, kind of interesting. It looks like there's some emission here, some absorption here. Don't don't really know, you know, how much of this is real and how much isn't. But I would think that these are calibrated, which means that you know they've gotten rid of all the junk. So I would say that most of this is you know really coming from the star, and so we've got some you know some narrow emission lines here, some broader lines. Pretty complicated, lots of stuff. We're starting to look at, I mean, when you get this long of a wavelength, you're starting to look at molecules and all of that. So yeah, pretty cool though. Spectrum. Validation status, scientifically validated. Well, hey, the high priests have spoken. So there you go. It looks like this is, yeah. So this is from the Infrared Space Observatory. Very cool. Let's look at a little bit more of this data. These look like spectra again. Okay, so there's, wow, so even longer wavelengths, 100 micron. Wow, okay. So they're looking at things, getting into the sub-millimeter range, right? Because what, 100 microns is 0.1 millimeters, right? So yeah, that's getting pretty long wavelength there. Still some interesting structure there. Now, I'm not exactly sure what all these different colors mean, whether that is a different instrumentation, different data set. I'm not exactly sure. Let's look at a little bit more here. Okay, so here's just a different data set. Looks like it's the same wavelength range as we saw before. I can sort of see, the same structures here, this narrow band one, this wide band emission here, wide band absorption here, something funny there. I don't know if that's a bad data point, but you really shouldn't have negative flux. That's sort of scientifically validated though. So yeah, I guess the high priests have spoken on that one too. So let's see. Can we? Oh, it looks like there's an images. I don't know. Let's find out. Taking its time. Taking its time. Clock is ticking here, people. There it goes. Oh, uh-oh. Trouble in paradise. Let's see. Let's try another one. Let's try this one. I'm just randomly. Yeah, it looks like. Oh no, is it? Is it going to do it? No, it looks like that. No, it looks like this site is having trouble, temporary trouble. So let's go up to the papers, the references, and see what they're talking about here with this variable star RR Telescopium. Pretty recent papers, 2018. XMM Newton study of the super soft symbiotic system Draco C1. See, this is what I mean. Every single paper is like a jumping off point. I have no idea what a super soft symbiotic system is. But if I wanted to find out, I could probably, go to that paper and find out. So I'm not exactly sure why there would be a reference to IRIS in here. IRIS is a spacecraft. It's actually an 8-inch telescope that is looking at the sun. So Hip, you're jumping in. All right, plug your nose. Close your eyes maybe for a little while. Yeah, I'm not quite sure why there would be a reference to that star here, but maybe there is. Accurate pre and post eruption orbital periods for that, the evolution of close binary stars. So maybe RR Telescopium is a binary star. Wouldn't be too surprised. Symbiotic binary. Uh, Now let me just do an actual search for Telescopium. Oh, here we go. XMM Newton observations of RR telescopii, evidence for wind signature and shock gas emission. Cool. Should we dive into that one? Yeah, why not? Maybe they'll tell us a little bit about it. Okay, so RR, well, here, let me pull up the paper and we can read the abstract from the paper itself. So we're going to go to the ADS here, and hopefully there's a PDF file freely available. There better be. Looks like it is. My apologies for slow internet, but that's what happens when you live out in the middle of nowhere. I'm actually at the end of the line here. So, yeah. All right. So, RR telescopy is the prototype of the symbiotic Nova class. Since its outburst in 1944, okay, so it actually, sort of had a little bit of excitement back in 1944. It's been slowly fading, and its emission line spectrum has evolved significantly. Um, in this paper, we discuss um, XMM Newton observations of RR taken in April 2009. These are the first X-ray. Um, okay, so yeah, they're looking at this apparently in the X-ray. Provide important information about the physical conditions of the emitting gas. We have estimated the temperature and luminosity of the hot star to be 154,000 K and 5,000 times the luminosity of the sun. Holy moly! Um, uh, let's see, normalization of the models with the far ultraviolet flux leads to similar values. Both the shape of the low resolution X-ray spectrum and the spectral diagnostics that make use of the emission lines present in the RGS spectrum indicate the existence of collisionally ionized gas. At least two components are present with a temperature of approximately 0.6 and 1.7 million Kelvin. The existence of a wind from the hot star is unequivocally confirmed by HST STIS observations taken in 2000, which shows displaced absorption components for the nitrogen 5 and calcium 4 doublets. These components have terminal velocities on the order of 400 kilometers per second, which is consistent with the temperature of the gas detected in X-rays. So, okay, so RR Telescopy is one of the best studied symbiotic stars. Very cool. And it's a prototype. Its outburst started October 1944, and it reached a maximum brightness of magnitude 7. Wow. So, I mean, it increased brightness by 7 orders of magnitude. So that's 2.5 to the 7th. To the 7th. So that's 610 times brighter. So it increased its brightness by a factor of 610. Wow. And it stayed at that brightness for like 5 years. And then it's just been slowly getting fainter and fainter and fainter. At least according to this thing, it's at a magnitude of about 12 right now. So, but okay, but it's also a Mira variable. Okay, so it's not only a symbiotic star, but at least one of the components, the M star, is also a variable star. So, woo, it's complicated. Let's see, they estimated that it's at a distance of 2.6 thousand parsecs. Let's convert that to light years. So a parsec is 3.26 light years times 1,000. So that's 3,260 parsecs. And then times, what is it, 2.6? 2.6. So that's 8,476 light years away. So that's pretty far. That's pretty far. To be able to see that at all, it does have to be very bright. Yeah. I mean, what was it? 8,000? Yeah. 8,500 light years away, and it's 12th magnitude. Wow. Yeah. That is a bright freaking star. Um, let's see. Okay, so the binary. Oh, okay, so it's a white dwarf. Presence of a white dwarf, and an M star. Very cool. Um, okay, so the orbital period and distance between the two stars remain unknown. Unknown. Is extraordinarily rich. With emission lines. Yeah, the spectra that we were looking at before was just the infrared, right? I didn't click on any of the spectrum in the optical or the ultraviolet, but they say here that it's extraordinarily rich, uh, undergone remarkable changes. So not only is the spectrum very, very rich, it's changing. It's changing. So they're seeing new stuff. Very cool. They saw it back in 1984 for the first time with X-rays. Let's see. So this is an X-ray spectrum here. More X-ray spectra. You can see that these are in wavelengths of angstroms now. So I think this is, I guess I would call that ultraviolet. Yeah, well, yeah, I don't know. Very, very, very short wavelengths. But yeah, they've identified, here, I can zoom in here. They've identified these emissions, right? This is oxygen 7, oxygen 8. So that's 8 times ionized oxygen. That means that it's missing, the oxygen atoms themselves are missing 8 of their electrons. I think oxygen only has 8 electrons. So this is just an oxygen nucleus. That's all it is, right? It's really, really bright. Um, let's see, oxygen 7 again, oxygen 7, oxygen 7, oxygen, or nitrogen 7. So nitrogen 7, that is just a nitrogen nucleus. Very cool. To be able to knock off 8 electrons off of a um, oxygen atom, that takes a huge amount of energy. So the fact that they are seeing that is pretty awesome. See, nitrogen 6, nitrogen 6, nitrogen 6, carbon 6. So fully ionized carbon too. Holy moly. Yeah, this thing is kicking ass. So yeah, I think what they're saying here is that, you know, I mean, it is weak. It's not as if all the carbon and all the oxygen and everything is ionized, but some of it is. Some of it is. Mm, okay, so this is just a more detailed look at things. And we astronomers, we like to create models. So that's what this blue line here is just showing, you know, a model spectrum based on, you know, different parameters, you know, temperatures and masses and various things, you know, that go into the models, just to create a spectrum, just to sort of try to match up what the observations are, and you can see those observations there. Pretty big error bars too. That's what these vertical lines are. Yeah, so pretty big error bars in the measurement. But I like to see error bars, right? If it's just points here, it's like, you know, you guys haven't really done your job, right? You got to measure, you know, your measurement error. You have to know what that is too, because it gives you a sense of how certain you are about the measurement you make. So you know, these error bars are big, but they're not bad. You know, they still give an indication of, you know, the shape of these lines. Let's see what else we got here. Determinations of temperature and radius. So yeah, this is like a seriously hot star too. Seriously hot. Well, if it's a white dwarf, for sure, it's going to be pretty hot. Lots and lots of work here. Okay, so we're getting into the ultraviolet here, it looks like. Um, well, okay, this this is sort of actually spanning quite a wavelength range, going from X-ray through ultraviolet, starting to get into the optical here, right? This is 1,000. This is probably 1,100. This is 1,200 angstrom. So yeah, I guess it's still towards the ultraviolet. Consistency of the extinction derived from X-ray spectrum with other determinations. All right. Detection of wind. Very cool. Nitrogen 5 and carbon 4 resonance doublets. Yeah, spectra spectra are the best way to really find out a lot of stuff. And it says that RR-TEL is still burning. Supernovae or symbiotic novae like RR-TEL represent a small subclass of the symbiotic stars. It's still burning. It erupted in 1944 and is still burning away. Yeah, very cool. Um, Slowness of the outburst should be primarily ascribed to the presence of an undermassive white dwarf in the system. Very cool. Uh, but yeah, it looks like a pretty interesting little star. And you know, as I keep saying over and over and over again, you know, these papers are like a platform, you know, to jump off into so many directions, both in terms of topics and in terms of history. Right, this list of references is a history lesson. So it, you know, it's every single paper is sort of multi dimensional that way. So, wow, I can't believe it's already been over an hour. All right, well, I definitely respect all of your time. So I am going to stop sharing. And I think actually, yeah. I'm getting the message from the mothership that it's time. It's time. Plus my coffee is cold. So definitely have to warm that up. I don't probably maybe because my tolerance for caffeine is relatively high. Caffeine just doesn't really affect me. It doesn't keep me awake or anything. I just yeah, I just like coffee. So yeah. All right. Well, I'm gonna get out of here for now. Hope that was moderately enjoyable. I think that's an interesting um, different segment that I can do from time to time. I try to mix things up. I don't want to do the same thing every single day. Um, you know, having a daily thing, uh, you know, could be relatively monotonous, but astronomy is such a huge, wide topic that I don't see monotony ever happening. As I said, I've been doing this for a few months now, and I don't think that there's been a lot. I mean, there is a repetition of sorts, but no, there's always new stuff um, coming up, and there's so much old stuff that it's just I'm never gonna run out. Never. There's not a chance. There's not a chance of that. I could spend 24 hours a day doing this, and I still wouldn't run out. So I'd be totally exhausted. But yeah, I don't think that's going to happen anytime soon. So all right, I'm going to get out of here for now. Glad you could join me. If you're new here, make sure to subscribe. If you haven't already, you can set your notifications to let you know when I go live every single day. But I do that at 2 hours UTC every single day. I try to keep it to about an hour. Sometimes that's a little bit less, sometimes it's a little bit more. We're just hanging out, talking astronomy, forgetting about the rest of everything else, and just thinking about the universe and how awesome it is, and how awesome it is that we can sort of think about these things. Carl Sagan said that we are a way for the cosmos to know itself, and I think that even now gives me goosebumps because it really is. It's a self-awareness thing that is so cool. It is so awesome, to contemplate that I I am as part of the cosmos, able to sort of think about myself in this way. So we are awesome. We are very, very awesome. And we have to realize this. We have to realize this. Otherwise, we're going to destroy ourselves. And as I said, it's a race. It's now a race between those who don't realize it and and those who do. And I don't know who's going to win. I don't know who's going to win. Whoever does, it's going to be pretty interesting. So, but I hope that we're able to figure it out before that button is pushed. And there's a few other buttons that are coming along too. I think AI is sort of the same thing. I'm sort of in agreement with Musk, is that AI, we should probably worry a little bit more about AI than what we are worrying about. I think that could get out of hand pretty quickly and pretty easily. So yeah, we need to keep a handle on that too. That's an awesome technology that is right. I'm thinking is right around the corner. So maybe not, and maybe that'll be the end of us. I don't know. I don't know. But all right, I'm gonna get out of here for now, and I will see you on the spin. Don't get dizzy. Hold on to your hats. It's a pretty smooth ride, but I will see you again in a little less than 23 hours. All right. Take care. Peace. Cheers and all of that. Have a great evening, a great day, and I'll see you tomorrow. Bye.